The last speaker, but not least, of course, the workshop is Anders Buch. I guess Anders got on my radar back when he was a student of, and he and Bill Fulton were cranking out their advanced analysis paper on privilege degeneracy loci. So that's how I first met Anders, I guess. And he's going to tell us about the Picard group of a Cominuscule Richardson variety.
Thanks very much. Thanks for this invitation to this great workshop. Thanks for the chance to speak here. Yeah, it'll be about Picard groups of Cominuscule Richardson varieties. Let X be a Cominuscule flag variety over a algebraically closed field, and for some of the things I'm saying, but really, whenever I say anything concrete, X will just be a good old Grassmannian. So, Grassmannian of M planes and Cn. It's a set of all V besides Cn, where V is an m-dimensional vector subspace. So the combinatorics of this variety is very much given by corresponding poset. I'll call it script px. So this one has m rows and n minus m columns, and as Lauren was saying, you should always use partitions, no matter what you do in the Grassmannian, unless you have a really good reason. Otherwise, use partitions. Alan and Terence Chow had a good reason at some point, but there are a few exceptions. Yeah, so there are other Cominuscule flag varieties, right? Here's the whole happy family. Grassmannian of type A give you a rectangle. Here's the Lagrangian Grassmannian of type C. Here's the maximal orthogonal Grassmannian of type D. And for quadrics, you have these shapes to work in. Then there are the exceptional ones of type E. And yeah, so Young diagram should be translated into a diagram of boxes in these shapes, where gravity is always to the northwest. So, oops. All right, let's just thank the organizers. This has been a great workshop. Like the chalk is awesome. And the food is even better than the chalk. And the talks have been even better than the food, right? It's a great atmosphere. Thanks very much. Let's give the organizers a hand. Actually, I think we should thank the problem session chairs Dao Ji and Patricia. Okay. All right. So no secrets anymore. Let's take it down. Yeah. So if I have a partition or a Young diagram, lambda sitting inside this rectangle, then yeah, there'll be a subset of the boxes, like for example these ones. And then a good way to think about that box is take the border that starts at the lower left corner, goes up to the upper right corner, and then you number the steps in this path, from lower left to upper right, right? So this is step number 1, this is step 4, this is step 6, and you get a corresponding vector space V lambda. This looks like an irreducible representation, but today it's just a point in the Grassmannian. It's just this span of the basis vector I, for which the ith step of this path goes up. Right, so there are exactly m steps up. So this is just a point of the Grassmannian. So I have some groups acting like E is GLN acts on the Grassmannian, and inside we have the Borel subgroup, upper triangular matrices, and the B minus will be the lower triangular matrices. I guess that's like that, and the maximal torus will be the intersection, of course, and the key fixed points of the Grassmannian. That will just be the set of all these special points V lambda, which lambda is a Young diagram inside the rectangle. Maybe I'll leave the pictures on a little bit. So we have super varieties. So x lower lambda, that will be the B orbit closure of V lambda, and x upper lambda, that will be the B minus orbit closure of V lambda inside the Grassmannian. No matter what anybody tell you, right? This is the one and only canonical perfect notation for black right. This notation is set up so that the dimension of its lower lambda is the same as the codimension of its upper lambda to the weight of lambda. That's just the number of boxes in the Young diagram. And the Buch order on these Young diagrams just says that mu is contained in lambda if and only if the super variety x lower mu is contained in x lower lambda equivalent to x upper mu containing x upper lambda. And again, if and only if the intersection x lower lambda intersect x upper mu is not empty. When it is
reversed because your dimension is going up, but
well, dimension is going up, right? So this is natural. Mu is contained in lambda if the
other one, dimension is going up.
I guess the codimension is this one has smaller codimension, so that should be larger.
Mu contained in lambda.
Yes, I think I wrote it right. Yeah.
So I agree with everything except how do you draw your Hasse diagram of Young's ladder?
Yes. That's your argument. That's your argument. Let's not discuss that. All right, so when this intersection is not empty, it's for the Richardson variety. This would be x lambda mu equal to x lower lambda intersect x over mu. It's not visible, right? This is defined when it's not empty. And what can we say about that? Well, it's irreducible. It is rational. This was proved by Buch, classical result. Richard proved something a little bit more general. It's normal. That's a classical result. You meet Ramanathan Brahmanan. Yeah, for Schubert varieties, to extend it to Richardson varieties, I think we also need Brion. So the goal of the goal of this talk is, maybe we'll go over here. Goal is to find the Picard group. Right, which is the set of all line bundles on the Richardson variety. Up to isomorphism, right? Group operation is tensor product that gives a nice abelian group. That is very important for understanding the geometry of a variety. Yeah. Yeah. If you want to understand a variety on its own right, without sitting inside anything else, probably the first thing you want to ask about is what is the Picard group? But other motivation, the thing that we start wondering about this particular problem is this work on classifying super varieties up to isomorphism. It started with Richardson and Slofstra. They could say exactly when two super varieties in a complete flag variety G mod B were isomorphic with some root and weight condition. And then later on, Tariq Raji and Beihong Xu, who is here, yeah, they did the same thing for Grassmannian, and then they bumped that up to classifying super varieties and Cominuscule flag varieties. That was joined with Richmond. And in all that work, it was essential to know what are your line bundles, right? If you know the line bundles, then and you can tell what the line bundles are just from the geometry, then you have a way to define invariance that definitely just comes from the geometry up to isomorphism without knowing if it sits inside a flag variety or not. So that was essential. Yeah, so that's some motivation. And well, the usual strategy is to say, well, when we have a normal variety, then the Picard group is always a subgroup of the class group of Bay devices modulo rational equivalence. And yeah, when I teach algebraic geometry, I motivate the class group by saying, well, that's a little more intuitive. You can work with divisors and poles and zeros of functions, and then you can often use it to figure out what are the line bundles, what is the Picard group. But the problem with that is I have no idea what is the class group of a Richardson variety. It's not known. So the idea to get to the Picard group instead then is to look at the first Chow group. Right, this would be the free abelian group generated by curves. Let's just say generated by curves in X and modulo rational equivalence. And you always have a pairing. I guess no matter how horrible your variety is, you always have a pairing from the Picard group and with the first Chow group into the integers, where you take a line bundle and a curve, and then you can restrict the line bundle to the curve, and then you can take the degree of that. Basically, this is an integral pairing. So, since you have such a pairing, you always have here, you always have a map from the Picard group of a variety into the dual variety, right? By the dual, I just mean the group of homomorphisms to the integers. And the idea is that this might also be injective. The Picard group might also be a subgroup of the first Chow group. Well, in good situations, there are certainly cases where this is not the true. For example, if I have taken an elliptic curve here, then the Picard group is the elliptic curve itself, which is a group cross the integers, and the first Chow group is just the integers. So certainly that is not an injective map, but it works out for Cominuscule Richardson varieties and beyond. I should also say something about what is known. So, summary of that is everything is known about super varieties and very little is known for Richardson varieties, as far as I know. But for super variety, say X lambda, well, we know it is a union of Schubert cells. Yeah, this is X nu not, this is just B orbit of the corresponding T fixed point, right? So that means that we get the Chow group of the super variety is equal to the singular homology group, at least over the actual complex numbers, right? So this one is just free abelian on the set of all these groups, classes of smaller super varieties. Yeah, so in particular, the class group is the codimension one Chow group. So we know the class group of a super variety. And Mathieu, this was in 88. He computed the Picard group of any super variety. And by the way, Mathieu, he was working with the Richardson varieties and arbitrary flat varieties. Today I'm only speaking about the Cominuscule case. So Mathieu took the usual approach, realizing the Picard group as a subgroup of the class group. But if you look what he actually did, right, and then he has to say which subgroup of the class group. Well, then he started looking at what are the one-dimensional super varieties, the super curves contained in your super variety. And yeah, then his statement might just as well have been, it might have been stated as the Picard group is just the dual group of the first Chow group. For Richardson varieties, well, again, Deodhar. This is it's a little bit earlier, 85, proved that prove that the Richardson variety is rational, right? So that means that at least the class group of the Richardson variety is finitely generated. Again, this is for Richardson varieties and arbitrary flag varieties. It's finitely generated. That's better than nothing. For example, that means that our Picard group is going to be finitely generated. And the only other result that I know about in this direction is Levinson and Prabhu. From 2019, they show that when X is the Grassmannian, well, then the class group of the open Richardson variety like this, the class group of the open Richardson variety is 0. What that tells you, well, then you can say more precisely which generators you can take. You can know the class group is of the whole Richardson variety is generated by boundary devices, but we don't know the relations. All right, so so then let's discuss some. Let's discuss Richardson varieties and Cominuscule flag varieties a little bit more. So, the Schubert varieties are given by stop diagrams of these shapes that gravitate to the northwest. Right, so that means that Richardson varieties will be given by skew diagrams. And I'll use the notation lambda/mu to mean the boxes in lambda that are not in mu. And then I'll use the notation that X lambda/mu, this is the isomorphism class of the corresponding Richardson variety. Why do I have to say isomorphism class? Well, if you look at the skew shape here, this is the skew shape. There are actually many Richardson varieties that give that skew shape, right? I have to choose a connection from here to the corner down there. But all those Richardson varieties, they are related by a translation by a Weil group element, right? So in particular, they give the same isomorphism class. So in fact, there's a stronger theorem, namely this X lambda/mu, this depends only on this diagram lambda/mu as a coset of long, short boxes. Right, this long, short boxes will, all these diagrams can be realized as sets of roots. And then in the non-simply laced cases, some roots are long, some roots are short. So therefore, you have to keep track of when we say lambda/mu as a poset. Right, that will be poset with the northwest to southeast. In the partial order, we have to keep track of which boxes are long, which boxes are short for this statement to be true. But the special case of this for Schubert varieties, this was the work of Richmond, Tarugarachi, and Beihong Su. They have it both directions, right? They have two Schubert varieties are isomorphic if and only if this poset they have the same coset. In this case, we'll have one of the directions, and there's an obvious converse. So, well, will hopefully be proved in the future.
By coset, you mean like the interval at Young's lattice?
Yes, yes. Well, actually, it's not really Young's lattice. It is Young's lattice, right? This lattice of boxes. Yes, yes, you're right. Yes, the interval. Although I guess it's not really an interval, right? This one has two minimal boxes. But anyway, it's a subcoset. Yeah, another relevant result that I did with Ravi Kumar in 2012. That was for classical cominuscule flag varieties. And that has a natural generalization to the exceptional cases. It says that if I let let's say this skew diagram is equal to theta 1 union up to theta r. These are the connected components. So we're going to have something like this in a rectangle. Yeah, so here we have theta 1, theta 2, and theta 3. Well, then the Richardson variety for this skew diagram factors as a product given by all the skew shapes of the components. Actually, now we have this theorem here. One example of that is if I roll this board down, I can take this skew shape here. All but the last box. This skew set here, that just gives you an E6 modulo P6. It's the Cayley plane. And why is that? Well, because this poset is isomorphic to this poset. Just have to flip some things around. So the Cayley plane, this guy is not a super variety in the Freudenthal variety here, but it is a Richardson variety. All right. Yes. Another theorem. Yeah. Again, if we have the connected components, well, then the first Chow group of the Richardson variety is equal to the direct sum of the first Chow groups given by the components. And similarly, the Picard group is equal to the direct sum of Picard groups. So I guess that reduces the case to looking at a Richardson variety that just has one connected component in its shape. I'll sack this now. Right, so what if the skew diagram is connected? Well, first of all, we have that first Chow group of the Richardson variety is isomorphic to the integers, just like the case for a cominuscule super variety.
Connected means edge connected, not just coordinate.
That means that the two boxes have to share side to be connected.
Yeah, edge connected.
Oh, that's what you mean. Okay, yeah. And this one is generated by class of C, where C is any stable curve, minimal degree in X. Yeah, and then for the Picard group, I then need to assume that not in type E. In that case, the Picard group of the Richardson variety is the dual of the first Chow group. Yeah.
What is the situation in type E?
What is the situation in type E? Well, I get to that a little later. Sam tells me that if you tensor with Q, then everything should be fine, possibly in characteristic 0.
Okay.
But in type E, well, this result here, that's actually true in type E. And why is that? Well, that's because either the skew shape is connected to begin with, and then it's vacuous, or the skew shape has components, but those components are so small that they all belong to cominuscule flat varieties of classical types. Like the same Richardson variety can be realized in a type A, B, C, D cominuscule flat variety. There I can handle it. Yep.
Do the parabolic subgroup, the T-stable curves that come from parabolic subgroups, do they have minimal degree? The edges in the GKN graph,
The T-stable curves that come from parabolic subgroups.
one parameter subgroups between T fixed points.
If they have no, it's the degree, a curve is given by a root, and the co-root give you the degree of the curve, right? So if the co-root is long, then the degree of the curve.
Length of one root.
Length one co-root. So you want a long root, it gives a small co-root, so that gives a T-stable curve of minimal degree.
So there's one kind of T-stable curve if we're simply laced, and two kinds if not.
Yes. Right, all curves are equivalent in the simple case.
Are these statements true like T equivariantly?
What do you mean by it?
Well, I guess are the line bundles the equivariant line bundles, the equivariant chart?
Yes, they certainly are. And that's the first result I need, namely Hirsovich. Proved that T equivariant Chow groups, as he defined them, are the same as ordinary Chow groups, but situations where you have a projective variety and a solvable group. So in particular, that means that this first Chow group is generated by T-stable curves inside the Richardson varieties. Right, and that's nice, right? Because there are not a whole lot of T-stable curves in a flat variety, and we understand them very well. They correspond to taking one fixed point and then a root, and then you have an S alpha that'll get you to another fixed point. There's a unique T-stable curve between those points. So that is nice. Here.
Still in the connected case.
So again.
Hershowitz is still in the connected case.
Oh, this is a very general result, projective varieties, and there's even a generalization to arbitrary algebraic schemes by Bill and Frank Sotilla and maybe McPherson. Forgot who the other co-authors are. Stonefields. Okay, sorry. So let's make the definition. If we have two fixed points, then we will say that they are adjacent. Well, if there is a T-stable curve through them. So if there exists an irreducible T-stable or curve Cx that contain them, the alpha and the beta should be in this curve. And for the Grassmannians, which I stick to when I say anything concretely, this is very easy to see. This is true if the dimension of the alpha intersect the beta is equal to m minus 1. Remember, I'm on a Grassmannian of m planes, so each of these vector spaces have dimension m, so they should almost be the same. Intersect has dimension m minus 1. Again, this is equivalent to dimension of their sum. Is equal to n plus 1. And then the curve, let's call this curve C alpha beta. Well, this is just a set of all V in the Grassmannian, for which alpha intersect V beta is contained in V, that is again contained in V alpha plus V beta. And then you will recognize this is just a P1 sitting inside the Grassmannian. All right, yeah, maybe we'll just do an example. At this point, I could take V alpha to be the span. Let me just write span with angles. 1, E4, E6, E7, and E10. And V beta could be the span of E1 and E6 and E7 and E9, oops, so 9 and E10. And I guess this goes on in Grassmann 5,12. And will alpha and beta, they index fixed points, right? So we should draw them with Young diagram always. And if we do that, let's see if I can draw a 5x7 rectangle here. Yeah. this one, and then alpha, alpha is taking step 1 up, and then it goes up at step 4 and step 6 and 7, 8, 9, and a 10. So this is alpha, and let's see, beta goes up at step 1, 2, 3, 4, 5, then it goes up at 6 and 7, 8, it goes up at 9, and then it just follows along alpha. So this is beta. Right, so alpha slash beta, right? This is this thing in here. And maybe you can see it. If they are adjacent, right, then you have to get from alpha to beta by just taking one of the basis elements and replacing it with something else. And that has the effect that when you get to step 4, right, one goes up and the other one continues. But then for a while they follow the same shape, and at some point they come together again. So that, we can notice that V alpha, V beta are adjacent if and only if the skew shape beta slash alpha, this is a connected ring. Up to maybe I have to interchange beta and alpha, they'll always be ordered. And when I order them right, then the skew shape is a connected rim. Right, this fact that the rim is connected has a lot to do why I split up in components. A connected rim can only be in one component. Another thing we can notice is that that this curve through V alpha and V beta is contained in the Richardson variety if and only if mu is contained in alpha, which is then contained in beta, which is contained in lambda. And then we have a lemma, two lemmas. This one, it's very much for cominuscule flag varieties. There are counterexamples in all other flag varieties, at least by computer check, but I'm sure you could write down systematic counterexamples. Except it's also true for flag varieties of type G2 or Picard rank 1 for some reason. But if I take beta slash alpha greater than equal to 2, right? So that means from alpha to beta, there's at least 2 levels up in the Buch order. Then there exists a gamma such that alpha is contained in gamma contained in beta, and such that V alpha, V beta, and V gamma, they're all adjacent. Pairwise adjacent. Right, so the picture of this, is that we had well, the beta sitting high in the Buch order, then the alpha is low here, and they're adjacent. So you have a t-stable curve through them. Then if you have at least 2 levels up, right, then you can find a point sitting in the middle, V gamma here. Everything is adjacent. So you have a triangle of t-stable lines in this case. So here,
An assumption in your lemma is that alpha and beta are adjacent.
yes, yes. Did I? Oh,
Maybe set up, you can write it.
oh, yeah. Yes, absolutely. Thanks. Then the other lemma, and this works for arbitrary flag varieties, but this time not in type G2. What does it say? It says that if you have V alpha, V beta, V gamma adjacent, if you have them adjacent, then there exists some omega in X that is closed and T stable with three properties, right? You have that the T fixed points of omega are exactly your three adjacent points. The curves through those points are contained in your omega, and finally, the first Chow group of omega is just the integers. And
Omega irreducible is that part of me?
yeah. Omega is irreducible. Yes.
Is it a weighted P2?
It is either a P2 or a super divisor in Lagrangian 2,4. Yep.
So weighted P2.
I don't know what cominuscule means. I know you said to just picture the Grassmannian, keeping in mind Lauren's caution from yesterday about there being too much structure when we picture something very friendly. Is there anything to say about which properties of the Grassmannian I should be keeping in mind?
I think the most important thing is that the Buch order is given in terms of shapes.
Okay.
That's very special for Cominuscule varieties, and it seems to be the root of goodness. Right.
Thank you, that's helpful.
Good.
Sorry, so what was the answer for Grassmannians? Is it always a P2 or?
For Grassmannian, it's always a P2. And let me just say what it is, right? Grassmannians is just instead of all V in your Grassmann M comma M, for which V alpha intersect V beta intersect V gamma is contained in V, that is again contained in V alpha plus V beta plus V gamma. Right. This is always isomorphic to a P2 because you can check the adjacency condition, means the dimension from here to here, dimension jumps by 3. So that's your P2.
Right. You didn't say, but omega is two-dimensional, right?
It's always two-dimensional.
And so here you don't mean all of these because well, they have to be n-dimensional. And so there's two options. Whether this is GR13 or it's GR23.
Yes, both can happen.
So in the Grassmannian, I know that there's finitely many T-fixed surfaces. Is that a Cominuscule fact?
Huh. I didn't know that fact. So I don't know.
There's these guys and there's some P1 cross P1s.
Maybe it's not surprising, but well, I didn't. I never thought about that. So application of this. Right. If I have a T-stable curve that's contained in my Richardson variety, well, then I take my surface omega from over there, and at least my points are contained in this Richardson variety, which implies, by result I proved with Pierre-Emmanuel Capru and Nicolas Perron, that what implies that omega is contained in the Richardson variety. Right, well, we proved that the Richardson variety is always T fixed point inclusive. Although Alan tells us we should call it T convex, that's a better word. What it means is that if you have any T stable closed subvariety of a Richardson variety, that all the T fixed points are contained there, and the whole thing is contained. So convex, yes, I'm liking that. And what does that mean then? Well, that means that you have that the class of C alpha beta is the class of C alpha gamma, and is the class of C gamma gamma beta in the first Chow group of omega, which is then a subgroup of the first Chow group of the Richardson variety by this forward. And what that means is, well, that means that if you have a T-stable curve like this one, you can get a smaller one from a smaller diagram. You can continue until you just have a T-stable curve for a single box. That's just a one-dimensional Richardson variety. And then again, this property says that all one-dimensional Richardson varieties have the same class inside that Richardson variety, at least as long as the diagram is connected. So, conclusion, the first Chow group of Richardson variety is the integers when lambda slash mu is not empty and connected. Yeah. Okay, so let's discuss then how do we go from first Chow group and to Picard group.
I'm really sorry. It's like the curve alpha beta is the class of alpha gamma.
Yeah, and it's also the class of C beta gamma, right? All the three curves have the same class, right? Because they live inside this. They live inside this first Chow group of omega, which is just the integers. I'm lying a little bit. In the other types, you have these equalities up to a factor of 2, potentially. But the point is that no matter what T-stable curve you have, its class is equal to the class of a one-dimensional Richardson variety. And then all the one-dimensional Richardson variety that live in the same connected component of the skew diagram, they have the same class. So here's another theorem. X is a cominuscule flat variety of type different from E. Then there exists a desingularization pi from the solution of singularities of the Richardson variety and to the Richardson variety. We know that. One gives an explicit one, but one such that the pairing of the Picard group with the first Chow group of the resolution is perfect. Yeah, so the way I cook up such a resolution is I make a resolution that's a tower of Grassmann bundles, and in the other types, so you also include Lagrangian Grassmannian bundles and orthogonal Grassmannian bundles. I wrote in my abstract that that resolution is interesting in its own right. stand by that. It's so simple that it wouldn't surprise me very much if it's also known, but I haven't seen it before. Well, hopefully I'll get to say very briefly how it works. Yeah, so in relation with this, right, there's an obvious question. Mainly if y is non-singular and projective and rational. Rational is important. Does that imply that the Picard group of y is at least a subgroup of the first Chow group? Well, the dual of the first Chow group. So I asked several people about this, and Sam had something to say. So, since this is true, if you tensor with the rational numbers, then I think you're using Hodge's theory. So I imagine that means we have to assume that we are in characteristic with 0. The resolution doesn't require any characteristics.
The resolution, you know it breaks up as a union of affine spaces and tori, and
I know about the brick resolution.
no. Yeah, that one, but just in general, we could have a T-linear variety. Sorry, not a T-linear, a linear variety. Is this one of those, like it has some paving by affine spaces and affine spaces across the line?
I don't know. I'd be interesting to hearing about that if there's just something that works in general. Anyway, the Richardson variety is normal. That means that if you take the push forward of the structure sheaf or any resolution of singularities, then you just get the structure sheaf of the Richardson variety. And what that means is that the pullback of line bundles from the Picard group of the Richardson variety and to the Picard group of resolution, right? This thing is always injective. Exercise, projection formula, easy. And well, then we have a nice commutative diagram. Right, we have the map from the Picard group to the first Chow group of the resolution. And this is an isomorphism. And we have the Picard group of the Richardson variety here, pulled back by pi. And this one was injective. And here we have the first Chow group of the Richardson variety. We have some map there, commute. Right, but this commutative diagram tells us this thing has to be injected. Dual. Oh, yeah, dual. Good, thanks. And I guess this map is forward, and then you have to dualize the push forward, so it goes the right way. Yes, thank you. And well, then we have injectivity. We also want surjectivity. Well, that's easy. We know what to hit. We have a lot of line bundles we can choose. So that's easy. So we end up concluding that the Picard group of Richardson variety is in fact, yeah. The dual of the first Chow group. Yeah, and I'm out of time, so yeah, I really like the resolution, but maybe that's for another time then.
Questions?
But Zolovinsky has this resolution of Grassmannian Schubert varieties that's small.
Yes,
Do you know whether yours relates to that?
I imagine it's small. At least it's very economical. I have to. I looked at the definition of small, and it looks complicated, and then I did something else. I don't know exactly what it means.
One question could be, does it reduce to Zolovinsky resolution?
I don't even know that.
Or is it the fiber product of two Zolovinsky resolutions? In the type N.
Yeah, well, this thing about just taking the fiber product is, I think I would lose knowing that I have a tower of Grassmann bundles. Yeah. Yeah, the same with the Brion's construction, right? You take a resolution of one super variety, you take a resolution of the opposite one, take the fiber product.
It's not iterated P1 bundles anymore.
That just means I could not easily tell what would the Chow groups of those things look like. Yep.
So can you always embed isomorphic Richardsons into the same product of two? Or
Yes.
they are identical?
Yes. And in fact, there's a mechanism that works more generally for arbitrary flag varieties. If you have any, well, let's say you have a flag variety and you have chosen your group acting on, and you have chosen your Borel subgroup and opposite Borel subgroup. Right, so you have a Weil group, you have simple reflections. Define a flag subvariety to be any Levy orbit of a T-fixed point. That's always a flag variety again. And it's also always a Richardson variety in the original flag variety. Well, say you have an arbitrary Richardson variety in any flag variety. Well, there is a minimal sub-flag variety that contains that Richardson variety. Right? You can work out what should the Levy subgroup is, then you just take the orbit of any T-stable point in the Richardson variety. So I call this the minimal embedding. And the thing that happens is if you take the minimal, the minimal embedding of a Richardson variety is what you ask for.
Yeah.
And it's also how, if you have many components, take the minimal embedding. That minimal embedding is actually a flag variety that factors itself, and then the Richardson variety factors with it.
Another question is that lemma maybe can work sometimes outside of Cominuscule case. The above.
This one,
Yeah, maybe it's not.
it is true, right, for many pairs of T-fixed points, but in all flag varieties that are not cominuscule and are not of type G2, I can find a counterexample for you. Yeah. And there's a particularly interesting case. See, or a little, if you take the Grassmannian of the isotropic two planes in a 6-dimensional vector space, non-degenerate symplectic form, then there's a 3-dimensional Richardson variety in here. I'm not going to start writing while group elements down, but there's a three-dimensional Richardson variety. That Richardson variety has exactly 6 T-fixed points. So, and there are exactly 9 T-fixed lines, T-stable lines in there, and those lines look like this. And so what that means is that this lemma that's true in all cases almost, it's true, but you don't get anything out of it, right? Because you don't have any triangles or T-stable lines in this Richardson varieties. So you don't get any information from that omega lemma.
Oh, I was asking about the lemma above.
Oh, that one, yeah.
Yeah, well, that was already false for lines in C3. It connects the bottom point to the top point. Which also has 6 points and 9 lines. And connected like that.
So, but maybe like other, like maybe co-adjoint G-mod P or something. They're talking.
Counterexamples in all flag varieties that are not co-minuscule up to as much as I wanted to check. I didn't find it a hugely interesting problem as soon as it looked like everything is just false.
One more question, maybe.
So can you simplify the statement a little bit, maybe just based on the Grassmannian case? So the Picard group is isomorphic to the direct sum of copies of Z, no torsion, right?
Yes.
What's the exponent? How do I decode the exponent from this? And the shape? The lambda mon mu shape?
Oh, you count the components.
Just the connected component?
Yes.
And I don't have to worry about the rim hook decomposition in the end. That's
No. No. Of each component give you a copy of C. So,
that's all cases in the end.
yes, all cases of co-minuscule varieties outside type E.
Apart from minuscule one, are there other flag varieties? Pro half order is a lattice.
I think minuscule flag varieties they have the same phenomenon. But then all minuscule flag varieties are also co-minuscule for a different group actually. The Richardson varieties are the same between the two. Well,
Let's think on this again.